today we have our honor to have the Professor Cheng, who is going to give this talk, Near Mass Degeneracy in the Scalar Meson sector, a challenge to the Koch model. So we know Professor Cheng for many years. Actually, in the past he did a lot of study on these B Meson, D Meson, and also the CT violation. So we have the rather a long history of cooperation. Let me, although probably I don't need to introduce him, but at least maybe some people are not do not know Professor Cheng. So let me briefly introduce Professor Cheng. Professor Cheng was got his PhD. He was graduated from the National Cheng University to obtain his bachelor degree. Then he moved to Purdue University and get his PhD. He got his PhD in 1980s. Then in 1987, he went back to Taiwan and became the associate researcher in Academia Sinica. Since then, he worked on this. He worked at that institute and did a lot of studies and also educated many young theorists. In 2012, he became the distinguished researcher in Academia Sinica. So it's really a very prestigious honor to get a distinguished researchership in this Academia Sinica. So it means that we can see Professor Cheng more in Taiwan. And today we hope he's giving this lecture on the Scalar Meson sector. So let's welcome Professor Cheng.
Thank you. In 2004, exactly 10 years ago, I was invited by Bob Xiongyi to give a talk here. I don't remember it's a series seminar or colloquium. But nevertheless, I remember that I give a talk on multiple quarks. Okay. Now today I'm going to say something about like a tetra quark, four-quark states. So in some sense, this is like a sequential of my talk 10 years ago. Okay. Wow. Okay. Time flies. Okay. This work was done in collaboration with is a very young guy, Yu Fusen. He's from Lanzhou University, and he reached the Academia Sinica in last December and January this year. He's very young. He is associate professor at Lanzhou University, and he's only 28 years old. Quite young. Okay. We know that in the quark model, we know that the hadron properties, hadron structure, and also its dynamics have been well described by the SU3 or SU6 quark model. Okay. And in the quark model, the strange quark is heavier than the light constituent, like up-down quarks, by like 150 MeV. And in QCD, strange quark is of order like 90 to 110 MeV. Okay. Now let's look at the spectrum, like the Schultz scale one and also the factor Meson. And the Schultz scale one, we know that the K-on, of course, is heavier than pion because it contains a strange quark. And the eta is heavier than K-on because it has a SS bar. Okay. You may ask that why the mass difference between K-on and pion is so large, because K-on is like typically 498 MeV. Pion is about 135 MeV. Okay. Well, actually, in the pseudo-scale Meson sect, it's better not to use quark model. It's better to use like a so-called chiral symmetry. In fact, this is a perfect place to determine the QCD quark. Okay. So you determine the quark, the QCD quark mass from the spectrum of the superscale meson. Now eta prime is very strange. It's a bizarre one because eta prime in the color limit, eta prime is as light as a pion. But experimentally, it's other one. It's the most heaviest one. In fact, this is a very famous problem in QCD, so-called U1 problem. This is a very serious problem in QCD. In the color limit, eta prime is as light as a pion. Okay, and today we know that. So we have to solve the UA1 problem. So eventually, it was solved by like to Hood. You introduce like a so-called instant time, instant time solution to resolve the terrible, horrendous UA1 problem. Okay, so eta prime becomes the heaviest one. Well, when you introduce the instant time, you solve the UA1 problem. You also introduce another problem, so-called Swan CP problem in the QCD Lagrangian. You will allow to have a GG tilde term, which violates the UA1 problem, CP problem. But CP problem is just a peanut because it's not because you don't see CP violation in your daily life, so you don't have to worry about the UA problem. Okay, let's look at the factor Meson sector. Okay, the omega is almost degenerated with the low Meson in the K star. Phi is the heaviest one because phi is made of SS bar, okay, the heaviest one. Okay, so let's turn to the other sector. The P wave, the Petty even star. Okay. Now, originally, naively, you would expect that the spectrum behaves like this one. Okay. The reason is F0 is made of SS bar. It consists of composed of SS bar. Kappa is like a chaos. Okay. You have one straight quark. Sigma is degenerated with A0. A0 like a pion. Okay. So you expect that the sigma is degenerated with A0. Okay. The two quark model. But experimentally, what you see actually is the other way around. Okay. Originally, you expect from the quark model, you expect that the shape is like a pyramid. But experimentally, actually, it's an inverted pyramid. Okay. So A0 actually is as heavy as F0, 980, and of course sigma, kappa is less heavy than sigma. So experimentally, it's opposite to what you expect. Now, what is a scalar meson? If scalar meson is made of is composed of two quarks, QQ bar, then it must have an orbital angular momentum in order for the parity to be even. Okay, unlike a pseudo scalar meson, pion, unlike the factor meson, like a low meson, they are S-wave states. Okay, now for the scalar meson, you must have orbital angular momentum. Now, experimentally, two nonets have been observed. One is the light nonet for sigma F0 980, kappa, and the NO 980. Sigma also is, according to PDG particle data group, sigma also is named as like F0 500. But usually I prefer to call sigma because it's more easy. And the kappa actually is called K0 star 800. Okay, so this is the first nonet. Okay, the second heavy nonet is like F0 1370, 1500, 1710, and also K0 star 1430, also A0 1450. Actually, it's not a nonet. It's like you have 10 states. It's a nonet plus one singlet. Okay, so you what you see is F0 has A0 is degenerated with A0 in terms of the mass. Okay, the mass F0. Okay, mass is the same. Also, you will notice that the sigma and the kappa are very broad because their decay width. I don't think this one's good. Do you have a?
Another one here, maybe?
Oh,
No, this is a normal pen. So.
maybe this one better.
Yeah. Sorry. Wow.
Well, let me use this one. Okay.
Classical one is always better.
So you see that F0 and the sigma and kappa are very broad. Actually, it's the mass, the decay width is almost the same as the mass. Okay. So we have two questions. We have two puzzles. The first puzzle is why is that the F0 and the A0 they are degenerate? They have the same masses. Okay. The second is why are sigma and kappa are much broader than the F0 980 and also A0 900. So we have two puzzles, and it is very difficult, if not impossible, to resolve those two puzzles in the conventional quark model.
Okay. Do this F0 500 and the kappa, do they confirm they are the states?
Yeah, yes. Pretty much in the past maybe 5 years or 10 years. Of course, experiment is difficult because of because of the both width, and it takes a long time to really pin down, to really identify those two states. It's very difficult for the experimenters like you. Okay. Okay. Actually, I just mentioned two puzzles. Actually, just one simple solution, very simple solution. In fact, this solution is sort of like a one stone, two birds solution. And it's proposed by Bob Jeffrey in long time ago, 1977. His suggestion is very simple. We know that in two-quark model you cannot solve the puzzles. So why not go to the 4 quarks? Okay. So for the A0, you just add a hidden strange sect, like SS bar. Okay. You just add hidden strange quarks. Okay. Now for the F0, you just add hidden UU bar, DD bar. So as a consequence, you see that naturally A0, of course, has the same mass as F0 because they have a strange quark, up quark, down quark. Okay. Now, secondly, we also can resolve the second puzzles. Now, you look at the sigma decay to like a 2 pi pi, or F0 decay to the KK bar. Okay. In those decays, you don't need the hard gluons. You draw the diagrams, and they are OCI allowed because you don't need to introduce like one gluon or two hard gluons, etc. So usually we call this is like a quark rearrangement. Okay, and in terms of nuclear physics terminology, we call this is OCI allowed, and some people call OCI super allowed. Okay, just 4 apart decays. Okay, so you expect that the sigma, kappa, F0, A0, their decays are very broad. Okay, but the problem for the A0, F0, A0 is as follows. Although the strong decay F0 and the A0 are allowed to decay to KK bar very prominently, very strongly, but you know the phase. The KL is what's the mass of the KL? 495 MeV. What's the mass of the F0? 980. So phase space is almost 0. Okay, almost no, very little phase space is available for the F0, K0. So as a consequence, its decay is prohibited, almost prohibited. Okay, so F0, so as a result, the F0 is mainly decay to pi pi, and the A0 decay to the pi eta. Okay, now let me go to the previous slide. So now we see a very funny thing. We have 2 nane. One is a light nane, one is heavy nane. So light nane is the light nane is composed of 4 quarks, so called tetra quark state. Okay. The heavy one is composed of 2 quarks, but 4 quarks is lightening to the mass of the 2 quark state. Is this possible? Actually, the answer is yes. There's 2 reasons. First of all, in the light nane, the 4 quarks actually are there in S-wave state. They are not in P-wave state. Okay? For the 2 quark state, they has to be in the P-wave state. So, the first of all, you don't have to pay the price of the potential barrier. You don't have to pay the price of the orbital angular momentum, which will cost you maybe 500 MeV. Okay, so first of all, for this one, you don't have to overcome the potential barrier due to the orbital angular momentum. Secondly, in the tetra quark model, you have a interaction so-called diquark, anti-diquark interaction. They have some attractive interaction, such that by the end of the day, this guy is lightening the two-quark state, even though each guy consists of 4 quarks. Okay, so very amazing.
But it can be calculated by using lattice QC.
Sure. This is the job of the Pingwei. Okay.
Yeah, but do we have the results from the lattice calculation if this a real tetraclock state?
Yeah, the situation is still not so clear at this moment because for this 4-quark state, okay, one needs to study the variational study and also well, I'm not sure it's completely the 4-quark state. Yeah, for the case of the D Meson you are going to mention, okay. Yeah, I can see the entire spectrum consistent with the experiment with just only the 2-quark interpolators. So.
Okay, we'll mention.
Yeah.
Okay, I just mentioned one puzzle about the near mass degeneracy. Actually, it's not the only place. There are several more. First of all, just a near degeneracy of the A0 1450 and the K0 star 1430. The mass of the A0 1450 is given this one. Okay, for K0 star is like a 1425. This is for the point of view of the quark model, sounds very strange because K0 star, just like KO, contains a strange quark. Why is it's lighter than the A0, like a pion? Okay, why is it light? Okay. Secondly, go to the Cheng Meson, scalar Cheng Meson. Okay, for scalar, the strange one is called 2317. Okay, spin major is the mass is 2317. Also the digital star 2400s. Okay, but the mass of the this one is 2317. Okay, the mass for this one is 2318. You may ask me the question, why is guy called 2400, not 23? This is a historical reason. Unfortunately, historical reason. Okay. Anyway, you see the mass almost close, almost degenerate. Okay. Also, this guy, the mass is its mass is enormously smaller than what you expect from the quark model. Because in quark model, people have been calculated for a long time. It's about it lies in the range of the 2480 and to 2510 MeV. So in other words, the theoretical calculation is too high by at least 170 MeV to 200 MeV. Still too light. And so it's just a 2G degeneracy here. Okay. In fact, it has been calculated in the lattice calculation. In lattice calculation, the Kentucky group, they have calculated the mass of the A0, scalar 1, and the actual factor Meson A1 in terms of the quark mass, or in terms of the empire spherically. Anyway, it's the same. Okay. So when you calculate from the quark mass becomes smaller, you see that beyond this point corresponds to the strange quark mass. But from the quark mass is equal to ms. Okay. For the mass is beyond the strange quark mass. The mass of the A1 actual factor Meson goes down continuously, but the mass of the A0 levels off, meaning that the A0 mass are almost independent of the quark mass. From the quark is lighter than the strange quark. It's almost constant. It's almost SU3 independent. So in other words,
it's a quench calculation.
This is a quench calculation. Of course, it's done long time ago. It's 2006. This is the quench calculation. So the A0 1450 mass is almost independent of the quark mass from it is below the strange quark mass. So let me go to the previous one. So apparently just a good SU3 symmetry. SU3 apparently is a good approximation in the scalar Meson sector from the energies above 1 GeV. Okay. In fact, in the same lattice calculation I just mentioned before, they calculate the K0 star 14 to this one and the A0 figure. Also, it's good. I will not say evidence. It's good hint that they are made of 2 quarks because in the logical you use two quark interpolator. Okay. So this is unusual behavior. of course, it's a challenge to the quark model or lattice QCD calculation. In fact, in 2006, Ke Liu, Cheng, we studied the mixing of the quaternion with scalar group. Okay, and our starting point actually is very simple. It's very robust because in the starting points are model independent. The first one that we use is the SU3, approximate SU3 things in the scalar Meson sector. The second one is the lattice QCD result, namely the mass of scalar group is about all the 1700 MeV. Okay, so our approach for the mixing of the quaternion group is quite is more or less model independent. Okay. In 2003, Baba made a striking observation, which opens a new chapter of the hadron spectroscopy. In 2003, Baba observed this very narrow scalar Meson, DGO star 2013. Okay, the decay width is very small. Okay, this is very bizarre. It's very striking because it's much smaller than what you expect from the quark model. Okay, so because quark model, the quark model prediction is almost 170 to 200 MeV too high. Okay. Okay, so originally in the quark model, you would expect that this guy is very broad because its mass is above the decay threshold. Okay, so this guy can decay to the strongly decay into the DKO, Chang Meson and the KO. Okay, so the decay width is is very broad. Okay, of order like 200 or 300 MeV. But actually, experimentally, it's very, very narrow. The reason is the only allowed decay for this guy is to d pi, because it's below the decay threshold. The mass is below the decay threshold. So the only allowed strong decay is to d pi. But this strong decay violates isospin symmetry. You can check, okay? Because pion has an isospin 1. Chang doesn't have. Okay, so no, DS doesn't have. Okay, so it's a decay channel via the isospin symmetry. Okay, so let me show here. So in 2003, Baba measured the spectrum. You look at the invariant mass of DS50. Okay, look at the decay width is very narrow. Okay, so look at the with the very sharp signal here. Okay, at the mass like 2.3 GeV. Okay. So anyway, this is a very serious blow to the quark model because quark model you don't expect it. So a few weeks after the Baba's paper, George Hall and I, we are the first one to propose that perhaps this is a 4-quark state, it's a Tesla quark state. Okay, and the reason we propose this one is just like the story I mentioned before, that the light nane consists of the 4 quarks, but it's even lighter than the 2-quark state. Okay, so we made this assumption. Okay. And likewise, the digital stuff, the non-strange one, also is about 70 MeV below the quark model expectation. Okay, so in 2003, George Hall and I we wrote. Actually, this is our first paper collaboration. Okay, but it turns out that a few months later, we found out that actually it's not quite right for some other reason. Actually, the reason is here. So we have 2 problems. The first of all, why is the DS no? I will just call So I will just call it as a DS node. I will let's say DS node star 2370. Okay, just say DS node, and this is D node. Okay, rather than D node D0 star 2400. Okay. Okay, so we have two issues, two problems, two difficulties. The first of all, how do we understand the smaller mass of the DS node? The secondly, how do we understand the degeneracy between the DS node and the D node? Okay. So two issues. Okay. And this gentleman, the Minister Sinovich, okay, he proposed that he likes our model, like my model with George Hall. Okay. So he proposed that we have a 3 light quark, and the light quark transform is like a SU3 intertriplet, okay, 3 bar, 3 bar. Okay. So you can decompose it. Now, for the wave function in this anti-triplet, totally anti-symmetric anti-triplet, you can write down this favor wave function. Okay. And so now you can understand why this guy has the same mass as a DS node. D node has the same mass as a DCS node. And it's not true in our original paper, my original paper with George Hall. In our original paper, actually, they have a different mass. Because one has a straight core, the other one. The reason is in our original paper, we don't put the wave function, we don't put the vapor function in terms of this one. We just put it into H3, anti-triplet, not anti-symmetric anti-triplet. Okay. Also, originally we thought that the 4-quark state is lighter than the 2-quark state. But actually, it's not quite true because remember that I mentioned two conditions. One is orbital angular momentum. Okay, here you don't need orbital angular momentum. Okay, you don't need to overcome potential barrier. The secondly, you need some attractive interactions between the light diquark and the light anti-diquark. But here you don't have a light diquark because you have a Cheng quark and the others up quark. So they are not really light diquark. So actually, the Tesla quark is not lighter than the 2-quark state. Okay. So that's the reason that it's a gentleman, the Meson sandwich. He proposed that maybe the mass can be pushed down by the two-Hughes interaction. Okay. So many people like the two-Hughes interaction because it can do a lot of things. Okay, it can raise the mass of the electron, can lower down the Tesla quark mass. Okay, but this model actually has a serious problem because whenever you have a 4-quark state, you must also have 2-quark state. Whenever you see one state is made up of 4 quarks, there must exist another state made up of 2 quarks. So tell me, where is the 2-quark state? Okay, suppose that the Tesla quark is light as like 2317 MeV. There must exist a 2-quark state with the same quantum number. Okay, that state is higher, has a larger mass. Okay, so it must be heavier and much broad because that state will be above the decay threshold. Once you are above the decay threshold, then it will become very broad. Okay, but until today, we never saw another DS node state which is heavier, which is broad. No, we never see. So in other words, it's really a strong argument against the Tesla quark interpretation of the Cheng Meson, of the scalar Cheng Meson. Okay, maybe George Hall, he may not like it, but actually this is so. Okay, so just know. Actually, also you also need another Tesla quark state, like for the 6 state, 15 state, and actually, but experimentally we never saw the state. Now, next the second year.